Hi, Physics 1. Mr. Janowski again. This is part 2 of the Chapter 13 slides. In part 1, we covered literally everything that has ever happened. We covered everything from the moment of the Big Bang up until where we are right now. So in this part, we're going to cover even more, because we're going to cover everything that's going to happen from now until the end, the very, very end. So that's a lot. So let's get started. So to review, how long ago was the Big Bang? Do you remember the number? It was 13.8 billion years ago, this many years ago. So that is a extraordinary claim. So what's the extraordinary evidence we have for this? Remember, there are two pieces. The first one is the expansion of the universe, which we can give Hubble credit for this, even though he wasn't really the very first person to have this idea. Hubble's the first one to have evidence for it. So yeah, the universe is expanding. That must mean that before it was all closer together, and 13.8 billion years ago, it turns out, it was all right on top of itself. And the other piece of evidence is the bird poop story, the cosmic microwave background. So besides that, we learned that there are four fundamental forces in the universe, and all of the other forces we deal with are really just manifestations of those forces. Do you remember what they are? They are the strong and weak nuclear forces, or just called the strong force or the weak force, electromagnetism, and the force that is the main focus of this chapter, which is gravity. Far and away the weakest force, but still very, very important. It actually is responsible for all the large-scale structure of the entire universe. So you can watch this. I'll put a link to this in the slides, just to kind of review everything. Again, this is a real reason to love physics, because we get to zoom out and look at the entire universe and everything that has ever happened. And the entire universe and all of its history becomes our toy when we do this. So it's kind of fun. I'll put a link to this. Also, Crash Course, very good. It's not Hank. This is actually Phil Plait, an astronomer. It's a good one. And you might also enjoy this video. So if you can tell by the title, the first few moments that physics can't explain. So you might remember from the last time that physics doesn't know what happened from the time of the Big Bang up until 10 to the minus 43rd seconds after that. This is called the Planck Era, or the Planck Era, depending how German you want to pronounce the man's name. This is where our two best theories of what's going on in the universe, general relativity and quantum mechanics, they don't work together when you put them together, which we have to do occasionally. We have to do that when we're talking about black holes, and also when we're talking about the very beginning of the Big Bang. So that's the one part of the entire history of the universe that physics really just can't say what's going on. Everything since then, we have an idea of what was happening. But from this tiny fraction of a second after the Big Bang back to the time of the Big Bang, yeah, we don't know. So interesting stuff. I hope you find this interesting. I don't know what I would think of a person who didn't find this kind of thing interesting. Yeah, watch this video. I put a link. So, the fate of the universe. Last time we talked about the birth of the universe and everything that's happened up until now. So now we're going to talk about everything that will happen at the end. So follow along with this. Again, since the 1930s, we've known that the universe was expanding, and we know that it is still expanding. So we look at the galaxies, and they're moving further apart. So cosmologists looked at this, and they said, well, we can kind of imagine three different outcomes to this. So remember, the universe is all expanding. It's all moving apart since the time of the Big Bang. So it's all rushing apart, but there's also gravity. And gravity is trying to pull everything together. So it basically comes down to, is there enough stuff in the universe to pull everything back together, or is there not enough stuff? And everything will fly apart. So the three kinds of scenarios we have here are, yeah, here is the Big Bang, and the universe is expanding and expanding and expanding, and it certainly still is at the present moment now. We know that things are still moving apart. But the first scenario is there enough stuff in the universe so that with gravity pulling everything back together, gravity eventually wins and slows this expansion and brings it to a stop and then pulls it all back together until everything recollapses back on top of itself. And we have a name for this. We call this the Big Crunch. So that's one possibility. Basically, gravity wins. Let me skip the middle one. It'll make more sense if I explain the third one next. The third one is basically there is not enough stuff. So the universe is expanding, everything's moving apart, and there's just not enough matter in the universe. So even with everything in the universe pulling on everything back to get, trying to pull everything else back together, everything is moving apart too quickly, and kind of the Big Bang wins and gravity loses because there's not enough stuff. So everything moves apart. So this would be, first one is gravity wins. Last one is Big Bang wins, basically. And the middle one is it's a tie. So this is the critical universe. This is just, for mathematical rigor, I guess, this is just the idea that there is exactly the right amount of stuff in the universe so that gravity pulls everything, and again, it's basically a tie. It ends up being very similar to the last one. You don't get the big crunch. Everything still moves further and further apart, but at exactly the right rate so that it never comes back together, meaning if it were moving apart just a little bit slower, it would collapse. This is basically gravity ties the Big Bang. So these are the three possible fates of the universe. So think about it. Which one do you think is most likely? Will gravity win, and we'll end up, everything will recollapse back on itself in the big crunch? Will it be a tie, and gravity pulling on everything just kind of exactly cancels the expansion of the universe, but doesn't ever actually bring it back together? Or the third one is, does gravity lose and the expansion wins? So the universe just coasts on forever and never comes back. And we actually know the answer. And the answer to this question is possibility 4. Not only is the universe expanding and getting bigger all the time, it's actually expanding at an accelerating rate. This is fairly new information. We figured this out in the 1990s. So that might sound old to you, but this is when I was in college. Well, high school and college, actually. Graduated high school in 94. Yeah, up until this point, cosmologists were sure that it was one of these first three because we knew everything was expanding, but gravity was trying to pull it back together, and they weren't sure, well, is there enough stuff and it comes back together? Or is it a tie? Or is there not enough stuff and everything just coasts, forever? And they kind of thought it was the third one. So they were very surprised, starting in the 1990s, when they started looking at these distant supernova. This is the plural of supernovas. These are stars that explode. And by looking at these distant supernova in distant galaxies, they were able to figure out that not only is the universe moving apart, but it's moving apart faster now than it used to be. For some unknown reason, the expansion of the universe is actually accelerating. And they came up with a name for the reason. Perhaps you've heard of this reason. It is dark energy. This is what dark energy is. So you can watch this video. Obviously I'll put a link to this too. But basically, dark energy, different than dark matter. More on that to come. We have no idea what it actually is. The only thing we know is that something is driving the universe to expand at an ever accelerating rate. It's expanding faster and faster all the time. And it takes energy to do that. So something's doing it. So we call that something dark energy. But we have no idea what it actually is. So this, hopefully you will find an interesting little table here. This is all the stuff in the universe. So atoms make up less than 5% of the stuff in the universe. So if you look at the periodic table of the elements, that's the atoms. That's the stuff. So it looks, we used to, kind of think that's the list of all the things that there are in the universe, and it totally is not. Because it turns out most of the universe is actually dark energy. So how can I compare energy to matter? Well, I'm sure you've heard of E equals mc squared. Energy is equal to mass times the speed of light squared. Well, yeah, you use that idea. So we have no idea what dark energy is, but we do know how much it takes to drive the universe apart at the rate that it is, driving apart at the rate that its expansion is accelerating. So we know how much dark energy there is. We just have no idea what it actually is. And this we just found out in the 1990s. Now, dark matter is a different thing. And don't be misled by the fact that they both have dark in their names. They're probably not related at all. And in fact, they actually kind of do different things. Dark matter we've known about for a very long time, since like the 1930s. Dark matter is, if you can picture a spiral galaxy. So just picture a galaxy like, our own Milky Way, and that galaxy spins around. And what dark matter is if you look at that galaxy and you measure the rates at which all the different stars are moving around, you can do some pretty complicated, math and figure out, well, how much mass does there need to be in that galaxy to make these things move around that way? Because ultimately it's going to be gravity that's holding the galaxy together. And so how much mass do you need to have enough gravity to have the galaxy move that way? And so it's complicated math, I'm sure. I have no idea how it's actually done. But people smarter than me, they do it, and they figure out how much mass there needs to be. And then they go back and they look at all the stars and they count up all the stars. And it turns out there's not nearly enough stars there. There's not nearly enough matter or mass that we can see to account for all the gravity that has to be there to make the galaxy spin that way. So, yeah, that's what dark matter is. So dark energy kind of drives everything apart faster and faster. Dark matter just kind of, it holds galaxies together tighter than we really have any reason to believe they should be. So yeah, they're both called dark because we have no idea what they actually are. Maybe they are related, but it doesn't seem that way. But nobody really knows. The key idea out of this slide is, yeah, we're physicists and we get a reputation for being kind of arrogant. Well, here's us being extremely humble. We will tell you right off the bat, we only understand less than 5% of the stuff in the universe. And the other 95% is just a total mystery. So if this were a test, we're getting a 5% on it. So there's lots and lots of room for improvement. And if you're looking at this pie chart here, there are so many Nobel Prizes to be won by figuring out what these things are. So yeah, dark energy and dark matter and the ultimate fate of the universe. So now finally, we get to the start of chapter 13, midway through the second part of the slides. Universal gravitation. So here's your formula for Newton's law of universal gravitation. And what this says is there is a gravitational attraction between any two bodies with mass given by this formula. So F sub big G, this is why earlier F sub little g, that's F sub little g equals mg. That's a different formula. This is F sub big G. And F sub big G is equal to big G, this is the gravitational constant, times the mass of one of the objects, times the mass of the other object, divided by the distance between them squared. So this is your law of universal gravitation. Might look a little scary the first time you see it, but it's actually a very beautiful and elegant little equation that tells you a lot. So if we're looking at this, notice that big G has a very small value. So 6.67 times 10 to the minus 11th. So yeah, there would be, if you move this decimal place over and kept moving it, there would be 10 zeros after the decimal before you got to this first 6. So this is a very small number. The smallness of this number accounts for the fact that gravity is so very weak. If this were a bigger number, gravity would be very strong and the universe wouldn't work the way that it does. But this is a very small number. This is just a number that describes the strength of gravity, and it ends up being a very small number. The other thing is this is proportional to the distance between them squared, or it's inversely proportional to the distance between them squared. And the squaredness is important. This is what's called an inverse square law. So yeah, D is in the denominator and it's squared. So what that means is if D starts to get bigger, then f sub g starts to get small very quickly because this is getting bigger and it's getting squared in the denominator. So this is an extremely make me one with everything kind of idea. Everything in the universe is pulling on every other thing in the universe. I mean, I've told you this before when we first started dealing with gravity, but literally everything that has mass is pulling on every other thing that has mass. Even though we are social distancing right now, you and your mass are still pulling on me with my mass and every other student with all of their masses throughout all of physics. You're pulling on, the Earth right now with your gravity, and the Earth is pulling back on you with its gravity. And you're pulling on the moon, and the moon is pulling on you. And if you walk outside at night and look up at the stars, you see those little points of light. The stars are pulling on you with their gravity, and you're pulling back on them. And every single thing in the universe is pulling on every other thing in the universe. So, yes, this is a very, very big idea. So, to review, what are the two main pieces of evidence we have for the Big Bang? The expansion of the universe, which Hubble came up with, and the cosmic microwave background, which Penzias and Wilson came up with. So that was from the last part. In this part of the slides, back in the 90s, astronomers expected to find, and cosmologists expected to find that the universe was either recollapsing, critical, or coasting, and they kind of assumed that it would be coasting. But much to their great surprise, they found out it was something else. What was the thing they found out? The universe is expanding at an accelerating rate. So not only is everything moving apart, but it's moving apart faster and faster all the time. And what is the thing that causes this? What thing causes the universe to expand at an accelerating rate? Dark energy. And nobody knows what it is. So, what is Newton's law of universal gravitation? So what's that formula? See if you can just picture it in your head. It is F sub g, it's force, it's a vector, and this will be force in newtons, is equal to big G, the gravitational constant, times the mass of one of the objects, times the mass of the other object, divided by the distance between them squared. And again, what a one with everything idea. What a poetic idea. Everything in the universe is pulling on every other thing in the universe. So, big, big idea. So that's it. I mean, that is literally it. In part one, we covered everything from the birth of the universe up to the present day. And in this part, we covered everything from the present day until the eventual end of the universe. You now know how the universe will die. So hopefully you find that interesting.